So as you see, it's better to just type check system and not execute them, because then you have problems. So now that we have some displays working, we can start. So the first talk is going to be presented by Gowtham on a novel approach to specifying inductive types that can be safely merged. So,
thanks, Eric. So I'm going to talk about a class of data types that can be used safely in a distributed setting. So these are replicated data types. So I'm going to define what replicated data types are and then present our work on mergeable replicated data types, right? Okay, so first, what are replicated data types? No, even before that, first let's consider why do we need replication, right? So the modern applications such as Facebook, etc., so they replicate the application state across various geographic locations for various purposes, so to ensure fault tolerance, for trust decentralization, but most importantly, to ensure low latency and high availability, right? So by locating these replicas, the servers close to users, you can ensure that the request can be served with low latency, and also even in cases when there are let's say network partitions, the users can still reach the local replica and therefore have access to the service with high availability, right? So to summarize, low latency and high availability are sort of twin motivations to get for replication. So just as a normal application, a centralized application, is organized in terms of various data structures, you can think of a distributed, a replicated state decentralized application to be organized in terms of various data types, data structures, which are essentially objects of replicated data types, right? So these are essentially what replicated data types are. And since the goal of replication is to ensure the independent and simultaneous progress at various locations. So these replicas of data structures, replicate data structures, need to accept user requests independently and have to accept updates. So what happens is momentarily these replicas may diverge, right? So you have the replicate data types, the objects of replicate data types, which have momentarily diverged because instantaneous synchronization is not possible in this setting. So however, the updates are supposed to eventually reach all the replicas. So all the replicas of this data structure are supposed to converge eventually, right? And converge not just to any value, but to a value that actually preserves the effects of all the operations done so far. So the best way to capture that restriction is to say that the value has to be equal to a result of some linear execution of all the operations, right? So that's what replicate data types are, and those are the restrictions that we impose on replicate data types. And let's see how easy or difficult it is to build replicated data structures that conform to these requirements, right? So let's build a queue replicated data type, QRDT. But first take a look at sequential queue, the signature of a normal, regular, everyday sequential queue. So here I show it as an OCaml signature, but it could as well have been a Java interface. So the queue supports two operations, a push and pop. Push takes basically an element and a queue and returns a new queue that contains that particular element. And pop returns the head of the queue if one exists, otherwise it returns none. And of course it returns the tail of the queue as well. Right, now let's try to replicate this queue by essentially replicating the state of the queue across various different locations, all of which give the same interface as shown on the slide, right? So the difference, however, is that the operations now are of course applied to the local replica, but they are also the side effect of the operation is also propagated and applied at different locations, right, at all the replicas. So what this ensures is that any operation that is submitted at any of the replicas are eventually applied at all the replicas of the data structure, right? So okay, so this is good. So we have some version of QRDT, replicated data type. Now let's examine few executions of this replicated data type, QRDT, right? So let's focus on an execution that has two replicas of this queue. We start with a queue that has two elements, 1 and 2. So we are focusing on a timeline view of the execution where the time progress is down. So let's say we initially do a pop operation on one replica of the queue and simultaneously do another pop at another replica of the queue. So both pop the element 1. Now, since as I mentioned, the effect of each operation gets eventually propagated to all the replicas, both the effects, both the pop operations get eventually propagated to other replicas. They get applied to the remote replicas. So here in this execution, actually, we do the execution actually converges to a state that has the effects of both the pops, but it's not quite right because if you observe, the element 2 has somehow vanished from the queue without ever being consumed, right? So here we have some notion of convergence, and in fact convergence it does converge to a value which has the effects of all the submitted operations, and yet it is incorrect, because of the reasons that are not captured in this formal specification, right? So now let's consider another execution. So here we start with two replicas of the queue which has only a single element 1. We do two concurrent pushes. So pushes of operation 2 and 3, and if we naively just send the updates over to remote replicas, so what we have are that these push operations are essentially gets applied in different order. So we end up with queue that the two replicas that do have effects individually have all the effects of operations submitted so far, and yet they do not converge, right? So what this means is we cannot have a consistent semantics to describe this queue, right? So the state of the queue does not converge. Okay, so we have seen two executions, and so looking at clearly these executions are not are ideal executions, are not ideal executions. So what we can infer is essentially our attempt to build a QRDT has failed because the replicas would not converge, and even when they did, like in the first execution, the convergence state is not quite right because we end up losing elements that are never consumed from the queue, right? So looking at this, we might infer that Q is not a conflict-free replicated data type because its operations cannot commute. You can't apply them on in any order at all the replicas. And so we might infer that the QRDT with meaningful semantics in fact requires a global coordination, such as logs, consensus, etc. But this conclusion is somewhat premature because there do exist coordination-free QRDTs with meaningful semantics. So Amazon's SQS simple queue service is an example. So the Amazon's SQS is actually a replicated queue data structure. It has a non-standard at least once delivery semantics. So what it means is, first of all, it does the SQS does converge, and second, at least once delivery essentially means that each item in the queue is guaranteed to be consumed at least once. So you won't have executions such as first one where the element just vanishes out of queue without ever being consumed. It is not linearizable. It doesn't guarantee linearizability or even a semblance of linearizability, but it is still a useful semantics. Right. So it's in fact adopted widely, and the at least once delivery semantics has in fact been proven to be useful. Right. So but this looks all non-standard. Right. So bad executions 1 to 2 in fact are no longer admitted. But the real question as PL people is, okay, so this looks very arbitrary, and this looks like someone has looked at the bad executions and just reverse engineered to this particular semantics. So how could we have come up with this SQS style QRDT without actually going through all the bad executions first? Is there in fact, if you frame the question, in a different way, is it possible to derive these seemingly ad hoc queue semantics, at least once delivery semantics, from first principles, right? So that's the question. And in fact, turns out the answer to this question is yes. We in fact can derive this sort of the non-standard semantics for queue, replicated queue, from first principles. And this is essentially deriving such sort of data structures is going to be the focus of this paper, right? Okay. But for that, we actually have to, in order to enable this sort of derivation of data structures with ad hoc semantics, we actually have to switch our view of replication a little. So instead of thinking of replication in terms of operations and their effects at various replicas, we're going to think about replication much like how we think in a distributed version control systems, like Git, etc., right? So if we recall, I'm sure most of you are familiar with Git here. So if you recall in Git, we start with some version of the source code in, let's say, a master branch. and we, let's say we want to create a new feature, we fork off a new feature, fork off a new branch to create a feature. Development proceeds concurrently on both the branches. At some point, you might get an unexpected bug report. So you create a bug fix branch to actually fix the bug. And since you don't want to release a new feature with known bugs, you might want to merge the bug fix updates onto the feature branch, right? So if you look here, so essentially you have what is a distributed workflow, right? So operations happening concurrently and eventually getting merged to a value which reconciles all the updates, right? So if we focus on just the last merge, if you clear everything, so we have two concurrent versions, which have evolved independently from one common ancestor version, a first version of the master. And essentially both the updates, both the concurrent versions have been merged to create a common version that includes the updates from both the branches, right? Now, this is a workflow that is quite familiar to most of the programmers. Since it's, we are huge fans of this workflow and we have used it multiple times. So the thing is, why can't we switch the source code here with data structures, right? And think of branches as not just branches, but rather independent servers, right? So what we essentially get from here is a version control model of replication. So where essentially branches represent a single line of development on each replica, and replicas can periodically synchronize, just as you merge branches. Replicas periodically synchronize to create newer versions that include updates from all the branches, from all the other remote replicas, right? So that's the version control model of replication, which is key to derive these replicated data structures with ad hoc semantics, but ad hoc but useful semantics. So let's focus on the three-way merge, right? So as I mentioned, the synchronization between replicas involves merging a pair of concurrent versions in the context of the lowest common ancestor. So this merge logic is in fact what sort of separates a regular data structure from a replicate data structure, because if you know how to merge two concurrent versions of data structure, you essentially have the first approximation of a replicated data type, right? You can merge the concurrent versions to essentially have a workflow which is distributed in nature. But however, this merge logic could depend, it's not arbitrary, it depends on our data type. So as an example, let's consider set data structure, right? Sort of the most simple, very simple data structure. Let's look at an example that involves sets. So you start with a set that has 1, 2, 3 as initial elements, and you create two concurrent versions. In this version control model of replication, you basically create two replicas of this list of this set, with elements 1, 2 on one side and 2, 3, 4 on the other side. Now you would like to merge these concurrent versions, right? So these concurrent versions might have been created through some complex operation, user-defined operation that you might not know of. However, looking at the concurrent versions and comparing them with their common ancestor, you can infer the intent of the user intent, right? So here, for example, you can infer that the intent there on the left-hand side is to remove 3 from the set of elements, and on the right-hand side it's to remove 1 and to add 4, right? Now, you can think of merging as essentially preserving the user intent by essentially by not losing any of these updates. And if you actually formalize it, if you write it down, you get set merge function, which is quite simple, which essentially it includes the common elements of all the 3 sets. That means it doesn't have elements that are removed on the either side, and it does include the elements that are newly added on the other side, right? So this is very simple. This is just straightforward, the way to merge 3 sets, right? Okay, so this is simple enough, but how about a little more complex data structures, right? Let's consider a list. How about a list? How do we define intent and intent preservation? So if we try to naively extend the approach that we used for sets and try to define intent, we might come up with this notion of defining intent in terms of list operations and intent preservation in terms of operational transforms, right? Like, for example, insert at position I will become insert position J after transformation, etc. So if you this approach of using operations and operation transforms has been studied. and it has been found to be quite cumbersome and hard to generalize for arbitrary data structures, right? So we don't want to do that. We are instead looking for an approach that is generalizable, that can be used for as a recipe to come up with distributed variants of all the data structures. So an approach such as op transform, which is hard to generalize, is not something that we want. But however, observe that we already know how to merge sets. We have written a very simple merge function. If you can somehow encode a list using merges, using sets, right? We can just simply devolve the list merge operation to set merge operation and just get set list merge for essentially for free, right? So okay, so that's an observation. But for that to possible, you need to first it has to be first possible to represent a list in the domain of sets, right? Is it possible to represent lists in a set of in the domain of sets? That's what it is. In fact, it is we represent list in the domain of relations, which are essentially relations are just a set of tuples, right? So we define what we call as relational abstractions of list. So we define two relations, the membership relation and an occurs before relation, that capture the membership and left to right order properties of a list. So in terms of a concrete example, so if the list is just 1, 2, 3, you have the membership relation as just set 1, 2, 3, and ordering relation as the tuples 1, 2, 1, 3, and 2, 3, right? So these are the set of all the elements, the members in the list, and these are the set of all pairs x, y such that x occurs before y in the list, right? So observe that in this characterization of relations RMM and ROB, we can completely capture the essentially what the list, right? So that is, if you know the RMM and ROB relations of a list, we can essentially reconstruct the list. Or in other words, if two lists agree on RMM and ROB, both are essentially the same list, right? So we call that characteristic relations of this particular data type, list data type. So in RMM and ROB are related through a subsumption relation. So that's the only, they're not independent, that the only relationship is that. And so consequently, now that we know how to completely encode a list in terms of these sets RMM and ROB, you can now define list merge in terms of set merge operation over RMM and ROB, while ensuring the invariant, the subsumption invariant remains valid, right? So that's the idea. So that's the core idea. So let's see how that works out, right? So let's consider a scenario of merging two concurrent versions of list V1 and V2 in the context of their common ancestor, resulting in a version V. So we can define the set of elements RMV to be set merge of all the three the membership elements. So if you define it in terms of set merge, so essentially elements in L that are not deleted in V1 and V2 are contained in V. Elements newly added in V1 are contained in V. Elements newly added in V2 are contained in V, and nothing else is contained in V. So so membership merge is quite simple. When it comes to but we also have the order merge. So let's try to define a merge over the orders, right? So order is as well, it's a relation, it can be defined as a set. So we can also conceivably use a set merge operation, right? So we start with this naive set merge of the ordering relations of V1, V2 in the context of L, the common ancestor L. However, since as we mentioned, ROB it's not independent set, it actually depends, the occurs before relation depends on the membership relation. We need an intersection with RMM V cross RMM V. And even then, what you have is essentially an under approximation of ROBV, because V1 and V2 might contain new elements that were never ordered, and you have to order them in the final list V, right? So we covered quite a distance. We actually know what elements we have an under approximation of the ROB. If you can somehow make it extend it to get the full ROBV, you have RMM from the previous slide and ROB now. So you can put them both together to compute the final list, right? So that's so this is an example where you have the two versions of the list, and essentially ROB the final list can be 1, 2, 3 or 1, 3, 2, because 2 and 3 are not ordered. Right. So if you can order new elements using lexicographic ordering, then we essentially can deterministically come up with the ROB, the occurs before relation of the final list. And once we have that, we can use with RMEM to compute the final list, right? So let's see how this works out with the push the queue example. So we consider the example that we reconsider the example that we had initially. So now we consider it in the context of a version control system. So we have two concurrent versions, 1 and 2, whose ancestor is 1, 2. So if we try to merge it, essentially using RMEM and ROB, we get the correct merge as 2, essentially that the membership relation as 2 and occurs before as empty. And likewise on the other hand side as well. So the element 2 is still present in the queue even as it is still not consumed, right? So in the other execution as well, we essentially get something similar. So we have 1, 2, and 1, 3, and once we extend it, we actually have all of them, right? So that's essentially the intuition behind relational decomposition and using relations to come up with this. So we found that relation decomposition is quite a general idea. It applies to many data structures. Just the important thing is not to look at the details here, but rather to observe that actually such decompositions exist for all the data structures. It's also compositional. The example can be found in the paper. And we have this, we have this notion of mergeable replicate data type, which is version control, which we get by combining mergeable data type with version control model of replication. And to actually realize all of this, we build this infrastructure called Quark, which supports this mergeable MRDTs. It's an infrastructure which actually has a compiler extension and a standard library of various mergeable replicate data types, and also low-level libraries implementing persistence layer and the network layer. So essentially, the takeaway is that given a data type's characteristic relations, which are abstraction concretization relations, we can essentially compute the merge function. So here the abstraction concretization functions are simply take the data type from the concrete domain to the abstract domain and back. That's it. So you can essentially compute the merges of the relations, and and that's essentially what the MRDTs are. So right. So we have a set of applications that we have developed using this approach, and the details are present in the paper along with the performance results, etc. So to conclude, essentially we have our insight is that the replicated data types are essentially a combination of ordinary data types with three-way merges, and it all this insight is actually practical. It works in practice. We have an implementation of that in OCaml, so I encourage you to take a look. So that's all I have.
Thank you. Okay, so we have time for only one question while the next speaker sets up.
Thank you. I really like this work. It was very interesting. I have one practical question about it. So the other replicated data types, part of the reason that they can be efficient is because they only have to ship around the operations rather than the states.
Yes.
But here, when you do the three-way merge, you need your state and the one you're merging in, as well as the common ancestor.
Right. So that's a good question. So if you think about it, the similar sort of problem also arises in the context of Git, right? So because you have basically two versions and try to merge it. So the way version control systems and also us resolve it is by computing diffs instead of the actual data. Instead of sending over the entire version to a remote replica, we compute the diffs and actually send over the diffs. And these diffs can be very efficient. So we can talk about it. That's the statistics we have in the paper. So these diffs can be as efficient as sending the operations themselves. So it need not be necessarily inefficient than sending operations over.
The definition of merge has the states on it. So in practice, is a different definition of merge?
Right. I'm sorry?
Is there a different definition of merge rather than the one that you showed?
No, the merge will essentially remain the same because merge logic doesn't change. What has to happen is essentially the underlying layer, the network and persistent semantics have to compute the diff. You only need to reconstruct the remote, the version of the remote replica So essentially, at the high level, you can assume that there are all the versions present, but to reconstruct those versions, you essentially just need to send the diffs over.
Okay, I'm
so
sorry,
you won't have to send the
I
entire.
have to interrupt the discussion. We are running quite late. So thanks again, Gowtham, for the talk.
Thank you.
Let's thank the speaker.